Two. So we're going to use what's called Coulomb's law. Coulomb's law is just another formula. Okay, it's just going to be another formula. You're not going to have to memorize it. It's on your formula sheet. And you're going to just simply, using two different charged objects, compute the electric force between them. So the electric force of repulsion or attraction. So it's really important to recognize in this section, this is the very first time we're doing this, where a force can be a repulsive or attractive force. Gravity is always an attractive force. Gravity does not pull things apart. Okay? Gravity pulls things together. It's an attractive force between two masses. That's what gravity is. Whereas the electric force can be attractive if they're opposites, but it can be repulsive if the signs are the same. So let's start by taking a quick look at the actual law. So here's our law. You do not have to memorize the constants. Okay, the constant Kc is called Coulomb's constant. Okay, Coulomb's constant. It's got some wild units. Don't worry so much about the units because they're on your formula sheet. Just recognize that the units are all going to come from the formula itself. Okay, they're going to come from the formula itself. So in this formula, we've got some other variables that we have not seen before. We have not seen the letter Q. We have not seen the letter Q anywhere this year. Okay, believe it or not, even though it starts with the letter Q, Q stands for charge. Q stands for charge. So actually, usually I try to look up this stuff whenever I wonder why that is. I was just thinking to myself, but I've never looked it up. So if somebody wants to figure out why it's Q that's used as a variable, feel free to just Google that. I'm not sure actually. It might have to do with some sort of a Latin or Greek root for charge with the letter Q. But I don't even know if the letter Q is in the Latin or Greek alphabet. I'm not sure. But it's not the letter C for charge. The letter C stands for something later on in the year we're going to talk about called capacitance. And the lowercase c is the speed of light. So we can't use the letter C for charge. The letter Q was introduced. Joe, you got something for me?
Yeah, it's quantity of electricity.
Ah, that makes sense. Q for quantity. It's quantity of electricity. And is this somebody supposing it, Joe, or is this actually like an actual reputable source?
It's an archaic term for charge, quantity of electricity. You can find this term used throughout writings on electricity from the 18th to 19th century, including notable use by Franklin, Faraday, and Maxwell. Okay. Where it gradually becomes replaced by the terms charge of electricity or quantity of electric charge.
Okay. Very interesting. Yeah, so quantity, that makes sense for Q. All right, so Q1 and Q2 are two different objects. You have a positively charged sphere and a negatively charged object. They will attract toward each other. But if they're the same, they will repel from one another. What do you think R is? What do you think R is? We've seen R before. What do you suppose R is in this case? What do you suppose R is? God bless you. We've used R in a formula very much like this earlier this year. Chris?
Radius.
Not radius, but you're on the right track. Radius is a length. It's definitely a length. R is definitely a length. There was a formula with the force of gravity, G m1 m2 over r squared. Pretty much analogous to this formula. Chris, you want to take another stab?
The distance from center to center.
Yeah, very good, Chris. The distance from center to center. Okay, R is the same thing again. And because these particles are going to be considered to be so small, we're assuming everything is measured from center to center here. So it's really, obvious to notice the analogous nature of this. And let me point it out real quick in case you're not seeing it. The other formula that we're looking at that I recall from earlier in the year is this. Okay, remember that formula? That was the force of gravity, where capital G was the universal gravitational constant. So look at the formulas, literally. The beginning is a constant, right? Constant. The tops are properties of the objects. Charges in this case, masses in this case. And then the denominator squared is the distance between them squared in both cases. So I want you to literally see that these formulas are pretty much the same, right? There's really no difference in these formulas except one uses mass. Because mass is what gives us gravitational pull. Your mass is physically giving you a gravitational field around you. Now, if you had some sort of charge and you rubbed your foot on the ground, well, now your body has a charge. That's Q. You're giving yourself a charge as a result of that charging of your foot, like on the carpet, or if it's better with socks, not a shoe here. The charge Q is, again, a property of the object. These are properties of the objects. The front is constants. The denominator is simply distance. Okay, it's really not a new formula, just a new way of looking at it for a different kind of force. Instead of gravitational force, now we're looking at electric force. Let's jump right into an example here. Let's jump right into an example. Using the table, it says above, it should say below. I don't know why I wrote above. Dang. Using the table below, determine the electric and gravitational forces experienced between an electron and a proton of a hydrogen atom. So this is data simply for a hydrogen atom, where we have a distance between the two. Hello. Oh, I sent it in already. Oh, you know what? I replied to Steve's actually. I'm just thinking about it. They were all here today. Sorry, Steve. Thank you. So you have the charges on the electron and proton, and this is what we talked about in the last class. This number should ring a bell. We went over this. This was the fundamental constant from Millikan's oil drop experiment. He determined that every electron was a quantized value, meaning a certain value. So the electron, notice, is negative, the proton is positive. That's the only difference in charge. But look at the significant difference in the mass, right? You've seen this in chemistry before. The mass of an atom comes mainly from its nucleus, from the neutrons and the protons added up. Here's the neutron mass, here's the proton mass, and then look how little the electron mass is comparatively. 10 to the fourth smaller. 10 to the fourth is a big number. It's a 1 with 4 zeros after it, right? It's 10,000 really. So this proton is about 10,000 times more massive than an electron. And that's why you hear that electron really contributes almost no mass to the atom. Okay, the AMU, atomic mass units, are mainly comprised of the protons and your neutrons summed together. So this is the mass, and look at the little difference. You see the small difference here? That's a proton, and look, there's the neutron. A very small difference. And that little difference there is indicating of, well, I don't even know. I was going to say it's the fact that a neutron is like a proton and electron together, but it's not technically those two together. I'm not sure, but a neutron's a little bit heavier than the proton is. But the electrons are very light. Now, no charge on a neutron, obviously. Okay, it doesn't matter. So if we're looking at a hydrogen atom, we have the average distance between the actual protons and electrons. So this is from the inside of the nucleus to the actual valence shell of the electrons. How many electrons are there in a hydrogen atom? How many electrons? Yeah, just one. Not a trick question, right? Just one. So we don't have to worry about there being multiple. And there's only one proton also. So the charge on the nucleus is just going to be this charge right here. The charge outside of the nucleus is just going to be that charge right there. So these are my two charges, and this is the distance between them. Again, because I have one proton and I have one electron. If I had 10 protons, right, because your homework's going to give you examples like this, 10 protons, I'm going to take 10 times this number to see the charge on 10 protons. If there were 50 protons, 50 times this number to give me the charge on 50 protons. Okay, so again, I'm going to go ahead and use these formulas. Let's start with the new formula. And this is K, Q1, Q2 over R squared. Okay, K, Q1, Q2 over R squared. K is a constant. Again, you don't have to memorize it. It's a pretty easy one to memorize, though. It's 9E9, or 9 times 10 to the 9. Newton meter squared per Coulomb squared. Times the charge on each. Okay, so we've got negative 1.6 times 10 to the negative 19 coulombs, and then positive 1.6 times 10 to the negative 19 coulombs. All over the distance between them squared, which is given in the problem. You don't have to know these numbers. Okay, you have to be able to understand what they mean and what goes in what spot, but none of these numbers need to be memorized. This is given in the problem. The charges on protons and electrons is on your formula sheet. Coulomb's constant is on the formula sheet. The whole numerator is practically on your formula sheet. Okay, if you look at the bottom, just so you're aware of what I'm talking about, the letter K and the letter E are on your formula sheet. E stands for the fundamental charge. If it's an electron, you put a negative sign in front of it. If it's a proton, you leave it as a positive. But this is on your formula sheet at the very bottom. This is also there at the very bottom. Okay? Recognize my units. What's going to happen here? Meters squared right here. Meters squared down here. Cancel. Coulomb squared, and this is Coulomb times Coulomb. Those cancel. So what am I left with? If these units cancel, I'm left with simply newtons. And what am I calculating? A force. A force is measured in newtons. So my dimensions make sense for this problem. That's why the units of this are so complicated. Because the Coulomb square cancels with these 2 coulombs here, and then the meter square cancels with this meter square down here. At this point, it's plug and chug, but there's a lot of room for error because it's in scientific notation. So if I'm you, and if I'm even confused at the least bit, I would most likely multiply out my numerator, get an answer in my calculator, figure out the denominator, get an answer in my calculator, and then divide the 2 by using second answer or some storage feature. If you want to do it all in one line, you can. You absolutely can. Okay, but just be very careful because even down here, you're going to have to square something. So my recommendation to you would be to put a set of parentheses around each of your things. So I would do parentheses, 9, capital E, 9. Remember how to do this in the calculator. I've taught you this already. So 9, second EE, and then the number 9, close parentheses. Then go to this one, negative 1.6 E, negative 19, positive 1.6 E, negative 19. Do all of that, and then divide by the denominator squared. Take a minute to practice this, please. I'm going to put the answer up so you can check as soon as you get it. Feel free to check your number. And this is the number that I get when I do it. So if you don't get this, it means you're probably making a mistake somewhere along the way. Yeah, Joe.
Are M and M and over C, are those just units?
Yeah, units. Remember I said this is just a complicated unit. These guys are pretty simple in units, but this one has to balance the rest of them.
Oh, okay.
Cancel, leaving behind units.
Okay. So you're not worried about the units?
No, you don't have to obviously. Just like we've never worried about them. Yeah. Once you have everything's in standard units, you can just multiply through and divide through if you need to. Anyone have hard copies of homework? I'm taking your labs. Anyone have hard copies of homeworks? Hard copies? I don't think anyone in this section does hard copies. Homework? The lab you have with you? Get that. Don't forget, guys, labs, please. If you don't give them in to me today, get them in tomorrow. All right, if you already gave it, I have like 5 people that gave them. I have a stack of about 5 in my desk, so I can check which ones they are. Hey, when you're done with this, let's go to part B. I know some of you are still calculating. Let's go to part B down here now, and let's find the force of gravity also, because that's what it asked for. Okay, it says determine the electric and gravitational forces between these particles. So let's use G, M1, M2 over R squared. And G is 667, 10 to the negative 11. Oops. The masses of the electron and proton are given in the table. And it's all over the same distance squared. I dropped units there, okay? Notice all the units were consistent, so I dropped them. So take a look at the gravitational force as well. I'm going to check to see your labs will happen. Take a look at the gravitational forces there. I have Christian, James, and Will. For people that turn into the lab, just so you're aware. Thanks. For the gravitational force, you're going to get 3.6 times 10 to the negative 47. So let's quickly just discuss, and it's really actually not even the importance of the answer, it's more of the relative answer I want to talk about. Which of these numbers is bigger? of these numbers is bigger? James?
First one.
Yeah, the first one. Right? This is far larger. I mean, we're talking about, so although this seems small, times 10 to the negative 8, for a force at an atomic level, that's a pretty decent sized force. Look at the gravitational force between them. The gravitational force between them is far less significant than the electric force between them. So the thing that's stabilizing this is not gravity at a subatomic level. That's the key thing to indicate, okay? That it's really not gravity at an atomic level. That's really the thing that's keeping everything together, that's holding things together. This force is clearly insignificant when compared to this force here. Okay? Again, although this seems small, this seems like a small number, look at the relative difference here. Gravity is far less of a force than the electric force is at this atomic level. Now, at a macro level, macro, big scale, right? For us, gravity is the thing that keeps you to the ground. The electric force is not doing anything. You could charge something with a very extreme large amount of electric force. We are not charged ions. The electric force is not going to affect us. Okay, and I would even go into like things like magneto, but that's magnetic force, right? If you think about like X-Men and stuff. But this concept here, right, this whole idea is that there's so much more electric force. What is the negative sign indicating here? Because that's something that we always seem to have trouble with on the test. And when I get to the next couple examples, you're going to see why the negative sign doesn't matter as much, but for this one it does. Like, for example, when would this answer be positive versus negative? What made this negative? Look at the problem itself. What made this sign negative? Because this one's positive, right? Joe, what made this negative?
Maybe the direction in which you see.
Okay, you're on the right track, Joe. Rick? It's all right. Yeah, the electron is a negative charge times a positive charge shows negative. So, a negative and a positive, what do? What did we say? A negative and a positive, they're going to attract. So, write this down. When there's a two-particle system, because we're going to look at a three-particle system next. When there's a two-particle system, the negative sign here just indicates that it's an attractive force. For a two-particle system, a negative electric force simply means that it is attractive. A positive would indicate repulsive. A positive there would indicate repulsive. For a three-particle system is going to be different. We're going to show. God bless you. We're going to show that in a minute so you can see that. Let's move on to number 2. Hey, if you're having trouble getting these answers, you got to come see me at some point. Okay? I'm happy to go over this with you, like one-on-one for sure. So if you have trouble using your calculator to get those numbers, please come by and I'll discuss it with you. Example 2 says, determine the distance between 2 point charges of 50 microcoulombs and 40 microcoulombs if they exert a repulsive force on each other of 150 newtons. So right away, determine the distance. What variable is that? In these problems, what variable is distance? R. So let's go ahead and write R equals question mark. Our first charge is 50 microcoulombs, and I'm writing this out for a reason today. And the second charge is 40 microcoulombs. So right off the bat, look what I do right away. Okay, I don't sit there and wait and think, oh, what's micro? Micro is -6. Micro is -6. Milli is -3. Nano is -9. Okay, those are the 3 that you need to know for this section. Especially for charges. We're going to be looking at millicoulombs, microcoulombs, and nanocoulombs. So we have to consider they go up by 3s. 10 to the -3, 10 to the -6, 10 to the -9. It's pretty easy to remember if you remember they go by 3s there. And when you think of nano, think, oh, nanotechnology, that's like the new thing, right? Or relatively new, I should say. It's because we're be able to work on things at a smaller level. Nano is the smallest that we're going to use. There's also picos, 10 to the -12. We're not going to look at any of those. So the question asks us to figure out the distance if there's a repulsive force. Why would there be a repulsive force? Why not an attractive force in this problem? Why is the force repulsive in this problem? What do you think is the reason for that? Fiona, what do you think? They're both positives, and likes repel. Likes repel. So the force has to be repulsive in this case. So that's what we know. Our formula is here. Okay, there's our formula. And the question is, figure out the distance. Figure out the distance. So you can plug in everywhere and then go ahead and solve for r squared and then square root it. That works. I'm going to solve algebraically because I think this is pretty easy to solve algebraically. What's the easy way to solve for something algebraically when it's down here? I don't want it down here. Where can I move it?
Switch it.
Yeah, switch it with the FE. Very good. Okay, remember, a denominator to solve for can be a little bit tricky. Just remember to move it with the other side. So let's flip-flop these two variables. This becomes r squared equals kc q1 q2 over fe. Make sure that your c is written really small. A lot of you have been doing things where you write your subscript a little bit bigger. For example, vt, tangential velocity for circular motion. I can't tell you, like, there are about 10 people that put t there and then put the time in that place. T is not time there, right? T is a subscript. C is a subscript. Don't put the speed of light here. Some students would put 9 times 10 to the 9, and then they'll put 3 times 10 to the 8 for the speed of light. This is not C for the speed of light. Is that clear what I'm saying? Okay, this C is a subscript. It is not a variable. Or parameter, I should say. It's not a parameter. It's a subscript. So now we just plug in at this point and go ahead and solve. Okay, now our goal is to plug in. So we've got 9 times 10 to the 9. I've got 50 times 10 to the negative 6. 40 times 10 to the negative 6. All over FE, which is 150. Now, how do I get R by itself? What should I have done? Square root it. Let's go ahead and do that, please. Let's go ahead and put a square root around both, and we can just cross off the R squared part, or the squared part of R. Technically, it's plus or minus, right? You guys know from your math class, there's always a plus or minus out here. But because I'm looking for the distance between them, whether it's on the left or the right of it, it doesn't really matter in this case. It's the distance in general. So I'm only going to be focusing on the positive distance here. And again, for the sake of time, I know we've done this a lot this year. You should definitely be checking. But for the sake of time, I'm going to put what it comes out to be. Okay, this is what it will come out to be. My recommendation is you do all the work on the radical and then take a square root of your answer in the end. Okay, you can do it all in one line. You totally can. This is not difficult to do all in one line of code. All underneath the radical is fine. But if you find that you're struggling with inputting stuff in a calculator, I would recommend the numerator first, then divide by 150, and then take the square root of that answer. That would be my recommendation if you want to be safe when it comes to inputting in a calculator here. Okay, around 0.35 meters. I'm going to move on. So if you're not getting this and you're really, some of you aren't checking, some of you are. So if you're checking and you're not getting it again, please come talk to me. So let's quickly talk about some key things and get into the real tough stuff in the next. We're going to do one more example, and that's the tougher one. It'll take us about 10 minutes. So first, some key examples here. Some key examples. So it's the key ideas. It is a field force. Remember we talked about field forces in the very beginning of the year? We said there's contact and field forces. A contact force would be, what force is it when I feel resistance? Friction. That's a contact force. Tension involves contact. But electric force, if the positive sphere is here and the negative sphere is here, are they in contact? No. But they're attractive. They're pulling toward each other because they're opposites. And eventually they might contact one another. But it is not a contact force. It is a field force. Second, we already talked about this. Its formula is analogous to that of the gravitational force. It's pretty much the same formula as the gravitational force. K becomes G, Q becomes M, and they're both over R squared. Third, as opposed to the gravitational force, which is only an attractive force, the electric force can be attractive if the signs are opposites, or it can be repulsive if the signs are like. And then finally, on a small level, we should clarify this, by the way. On a small level, it is significantly stronger than the gravitational force. Okay, on a small level, or small scale. So for like subatomic particles, we're really referring to here. But for like you and I, like macro beings, people that are, or things that are on a bigger scale, even though this is really not big compared to the universe, we're kind of small when you think about that. But for us, our mass has much more effect than our charge. So our mass and the mass of the Earth together are what causing the gravitational pull, which is pulling me to the Earth, okay? Physically pulling me to the Earth. Remind me tomorrow, because I'm going to show you guys the demo of the Faraday's tail tomorrow. I'm going to show you a couple other cool demos. I was on ever start looking at cool science videos online and you just get pulled into 20, 30 videos. I know, right? Nobody does this, no one. But you just start watching one video and then you're like, oh, related videos, or just starts on its own, in the next video. So was it yesterday or Saturday? I probably spent 2 hours just looking at cool YouTube videos at one point. And one of them was 50 at-home science experiments you could do. And there were 10 good ones for physics. So 3 of them I was thinking about for this topic. So I'm going to show you a couple cool ones. And then I sent Mr. Joseph a bunch of chemistry ones. And I'm like, these are really cool. I think he would like them. But yeah, I'm going to show you a couple more of them tomorrow on the double. But remind me to show you an animation. I found a better animation of the milk and oil drop experiment. You can't really demonstrate it. It's impossible to demonstrate it. I can't show it to you. But there's some good illustrations of it. And I found a good one this week and it did a good job. So I'm going to show you that tomorrow as well. We have a lot of time tomorrow to go over these videos and stuff. So example 3 is a little bit trickier now. Example 3, instead of having only 2 particles, instead of having 2 particles, we have 3 particles now. We have 3 particles. And that's why this becomes a little trickier. It could be positive, negative, positive. It could be negative, positive, negative, positive, 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 positive. You see what I'm saying? There are many orientations in which you can put 3 particles now. So we have to consider that. So let's take a look at what the problem tells us, and then we're going to analyze this using a free body diagram. In the last example, we didn't have to draw a free body diagram because the charges were opposites, so they attracted. The other one, the charges were the same. They repelled. So the free body diagram didn't matter. But with more than 2 particles, let's write this down, with more than 2 particles, you need to use a free body diagram. Again, with 3 or more particles, more than 2, with 3 or more particles, you got to use an FBD to solve. It will really help you a lot. Now, when I said to you a minute ago that I kind of left some of the heavy math in the text, you're going to see why. So here we're looking at 3 particles that are all collinear. Collinear. Definition? Collinear. On the same line. Very good. On the same line. Geometry word, right? Collinear, on the same line. So if we look at an example, though, where the particles are at the vertices of a triangle, they're not collinear. And that becomes a lot more complicated because now we have to use sines and cosines. Okay, but we are looking at an example where they are arranged on a line. So collinear on a line. Let's go ahead and draw a line first. In your text, the homework for this says 3 particles are located on the x-axis, which means they're on the same line. Okay, is that clear what I'm saying? When you see that later, it means the exact same thing. It'll say 1 particle is at 2 on the x-axis, 1 is at 7, and 1 is at 12. So at a distance of 2, at a distance of 7, at a distance of 12 from what we would call the origin. Okay, for this example, it's a little bit different. Particle 1 is located 0.3 meters to the left of particle 2. All right, so for now, I'm going to put particle 2 in the middle. I don't know if that's right. And I'll put particle 1 to the left of it. I don't know where particle 3 is going to be yet. It might be over here, so I'll extend my line further. Maybe it's in between them, which would be a problem. Maybe it's on the right. Okay, so particle 1 is located 0.3 meters to the left of particle 2. Which, now when you see the word which, we're referring to particle 2. Particle 2, which is located left of particle 3 by 0.2 meters, which means particle 3 has to be over here now. Again, break down the problem. Particle 1 is located 3/10 of a meter to the left of particle 2, which itself, I should say maybe itself here, which is 0.2 meters to the left of particle 3. So this is my arrangement of particles here. I have the charges, so let's just indicate if they're positive or negative on the diagram. So particle 1 is a negative charge, particle 2 is a positive charge, and particle 3 is a negative charge. Those are the charges that are given in the problem. I'm not deducing this, it's given in the problem. Okay, I'm also given the values, but for now, I'll take care of the values in a moment. But for now, I just want to think about the signs. Why am I asking you about the signs, do you think, here? Why do I care about positive or negative charges?
Because statistic force is negative, that means then like they're attracted to each other, or if it's positive, then they're repellent.
So you're on the right track, Rick. The positive and negative indicates if it's attractive or repulsive. Let's leave it with that. It indicates if it's attractive or repulsive. And we have to think about what this problem is asking of us first, though. Okay, it's not saying find out the overall force, because we'd have, ready? There's a force between these guys. There's a force between these guys. There's also a force between these guys, right? There are 3 forces technically going on here. I don't know what I'm doing, so I need to read a little bit more about the problem to see what I'm doing. Okay? I see a couple hands, so I'm going to take questions for now. James?
Oh, I was just going to say.
Give me 1 sec. I'll get to you with the answer question. Okay?
No, it wasn't a question.
No questions at all? These are all answers?
Yeah.
Okay, go ahead. Start, James. What are you going to say?
That's what the third, so the sign matters because the first particle, they're going to be repelled, the second one will be.
Good. So look what James just said. He said the problem is asking about the third particle. About the third particle. I was going to take it 1 step at a time. James kind of jumped, which is great. So start by just drawing the third particle by itself, please, at the bottom. Only draw the third particle. This is where a free body diagram is going to be useful. This is where the free body diagram will be useful. James, what did you say about particle 2 and particle 3 together? Particle 2 and 3, what are they going to do?
Attracted.
They're going to attract each other. So if I'm trying to find the force acting, ready? The force acting on particle 3 from particle 2. Which way will particle 3 be pulled as a result, or pushed? Which way will particle 3 be moved as a result of particle 2? Will particle 3 be pushed this way as a result of particle 2? Or will it be pulled this way as a result of particle 2? Which of those 2 scenarios will it be? It will be pulled, because James said it's attracted, and that's what pulling you toward. So let's draw an arrow from our free body, from our mass in the middle, indicating that there's a force on particle 3 from particle 2. That's a 3-2 here. This designation of subscripts is pretty important actually here. So if you want to write down what this means, this is a force acting on particle 2, on particle 3, from particle 2. A force acting on particle 3 from particle 2. It's simply pulling it in that direction. So again, I'm looking at my signs, my charges, positives or negatives, to figure out this problem here. In a minute, we're going to do some math, and once we get to the math part, I'm going to drop all the signs. The free body diagram is going to be all that matters. Now, what other particle is acting on particle 3?
Well, wouldn't also the negative one be acting on?
Yeah, particle 1, the negative one over here. So Joe, if I'm particle 3 and I'm hanging out over here, and particle 1 is next to me, and it's also negative, we're both negatives. Do we want to be near each other if we're both negatives? No. So which way am I going to be? Am I going to be pushed this way, away, or pulled? Yeah. This particle is negative, literally, and I'm also negative, so it's saying, like, get away from me. I'm pushing you away. So I'm getting pushed this way from the other negative charge. So which way should I draw this arrow? To the right. To the right. So what I have here are opposing forces acting on particle 3 from particle 1. Again, this was acting on particle 3 from particle 2. This is acting on particle 3 from particle 1. Fiona.
Why wouldn't particle 1 be attracted to particle 2?
It would. To 2? It would. But are we asking about particle 2? That's a great question, because I was going to pose that at the end. We have not considered how these affect each other. That's the only thing we haven't considered yet. We considered how these affect each other and how these affect each other, but these is the third one, right? F12 is the last force we haven't figured out. We don't need it this time. If I'm looking at the force on particle 3, I don't care about 1 and 2 interact with each other. It's a great question. Okay, great question. I saw a second hand up.
Yeah, I just have a question. So what would you do with those two values? Like, are you trying to, like...
We're going to see if it's...
You
what,
put them together?
exactly.
Yeah.
Joe, what is this? This is a tug of war.
Yeah.
Right? It's a tug of war. If F32 is stronger, it moves left. If F31 is stronger, it moves right. So it's important to write yourself a little note now. When we calculate the forces, we're about to calculate the forces, we don't care about the negative signs anymore. We already took into account attractive and repulsiveness. We already took into account whether it's attractive or repulsive as forces. So when we do the calculations, which we're about to do right now, I don't care about negative and positive signs anymore because the free body diagram already took that into account. The free body diagram already is indicative of my direction being left or right.
So you're going to calculate F32 and F31 separately?
Yes, very good. I have to calculate F32 and F31 as two separate things. F31 is the force between particles 3 and 1, and F32 is the force between particles 3 and 2. And then we're going to see which is larger. Whichever is larger, it goes in that direction. So let's go ahead and write these down. F32 is going to be K times particle 3 times, that's particle 2, it doesn't matter, times particle 3, right? Multiplication is commutative, so it doesn't matter which way I do this. All over the distance between particles 2 and 3 squared. Okay, take a look at my math, make sure it makes sense. Again, write yourself a note, I'm not worried about the sign being positive or negative because I've already taken into account whether things are attractive or repulsive with my free body diagram. With a two-particle system like we did in the last example, the negative positive can play a role. But for this, we care about the free body diagram and the magnitude of the forces felt, not the direction with the negative positive. It's already in the diagram. The diagram shows me the direction, left or right. I don't care about it that way. And then F31 is 9 times 10 to the 9. Now this is going to be Q1 times Q3 now. There's Q1. Here's Q3. And now the distance between them is going to be 0.5. Okay, if you're not sure where the 0.5 comes from, just look at your diagram right here. Right? 0.3 plus 0.2 is a total distance of 0.5 meters. That's going to go in the denominator now. All right, what do we get as numbers? F32 turns out to be 2.7 newtons. And F31 turns out to be 1.2 newtons. Again, for the sake of time, because I know we would run out of time if I sat here and waited, we're not going to type all these in. You can practice typing them in as you're waiting, that's fine. Okay? But I'm not going to go through the math and get at those numbers. So which one's bigger? Clearly, the first one is larger, F32. So this is going to be pulled to the left more, isn't it? Think about it. It's a tug of war, and the person pulling to the left wins the tug of war. So when I think about the net force acting on it, here's what I can say. I've got F31 pulling right, F32 pulling left. So I've got F31, which is 1.2, minus F32, which is 2.7. So this will yield a net force in the end, negative 1.5 newtons. Which simply means that this particle, and I'll circle this in red so we know that that's the final answer. That's my final answer there. This simply means that the particle will move to the left as a result of the other two forces acting on it. Okay, again, because we get a negative 1.5 here, the negative sign simply implies that the overall force is going to be felt to the left. To the left. So tonight you need to practice this for sure. Okay, make sure to practice this. You have two scenarios. Scenario 1 is a two-particle system. The signs matter. Scenario 2 with a three-particle system, use a free body diagram. I would highly recommend that you start looking at your problem sets for stuff Those problem sets right now are due on Thursday. Okay, and that may not change. I don't think the test dates are really going to change, so consider it being due Thursday. So you have a lot of problem set work you could have done from the last sections in chapter 17. So you're going to have a decent amount, so start looking at your problem set. Don't wait until the last minute, please. Here's your homework, by the way. Okay, take a look at your homework. Make sure to write it down.